Please title these notes Limits 5 Notes, Continuity, and write today's date. By the end of this lesson, you should be able to use both graphs and limits to determine whether or not a function is continuous. Continuity is really important because most of the techniques that we've been learning about can only be used on continuous functions. We're also going to look at something called differentiability in the next lesson, which again, also very important because in order to use our techniques, we typically need to have differentiable functions as well. So let's start off with continuous and just say what that is. So continuity is the concept. We would say a function is continuous so the informal definition is that a continuous function is one that we don't have to lift our pencil or pen to draw. So for example, if I have my little axes here, if I'm going to draw a continuous function, I can just start here, I can squiggle around wherever I want, but I never have to lift my pen until I go off the edge of the graph. In contrast, a discontinuous function would be one like this. I start over here, and then I stop, and I lift up my pen, and I move somewhere else. And then I'm sort of going along like this, and I stop because there's a little hole or removable discontinuity. And then I go up to a vertical asymptote, and then I come from the other side of the vertical asymptote and head off. These are all discontinuities. Here, I'll put that vertical asymptote in there where we can see it. A function, please. A function doesn't have to be continuous or discontinuous overall for us to talk about it. We can also just say that a function is continuous on an interval. So a function is continuous on an interval if we don't have to lift our pen to draw it for that interval. Outside of that interval, anything goes. So for example, if we had something like this, let's say 1, 2, -3, -2, -1, we could say that this function is continuous on the interval from -3 to 3 because I didn't have to lift my pen there. To go from -3 over here, I did have to lift my pen. At 2, I had to lift my pen, but from -3 to 2, I didn't have to. So let's look at a sample problem on a graph. At what values of x is f of x not continuous? and let's call this f of x. So, what I'm looking for here is I'm looking for where I need to lift my pen while I'm drawing this curve. I have to lift it at x equals -3. I have to lift it again at x equals 1. And a final time to go over this little hole, this little removable discontinuity at x equals 3. The formal definition of continuity is a little bit different. It involves limits, which is why it's in this unit. A function f of x is continuous at x equals c if the limit as x approaches c of f of x equals f of c. So we saw this before with one of our previous limits lectures. Basically what this is saying is we find the left-hand limit and the right-hand limit. They'd better match. That gives us this overall limit at x approaches c. And this f of c is just saying that whatever the value is when x equals c, that had better be the same as this limit. And what that just means is it just means that we have, as we come at it from the left and we come at it from the right, we're approaching the same number. And that point, instead of being an open circle, that point is filled in. That's all that it means. That way we can move nice and smoothly across. So let's write down our procedure for finding this. First thing we're going to do is find the left and right hand limits. Second, we're going to compare them. Do they match? No. That means it's discontinuous. Yes. Go to part 3. Is the limit the same as the value of f of x at x equals c? If so, it's continuous. No, it's discontinuous. So let's look at some examples of that. Let's say that f of x is x plus 5 if x is less than or equal to 2. Let's say it's x squared plus 3 if x is greater than 2. And what we want to know is f of x continuous at x equals 2? Well, with it set up here, first thing we're going to do is we're going to find the left-hand limit. Then we're going to find the right limit, and then we're going to compare. So the limit as x approaches 2 from the left of f of x, we've got 2 here, so remember on this side our equation is x plus 5, f of x equals x plus 5. On this side, f of x equals x squared plus 3. So if we're on the left-hand limit, we're looking at this one. Substitute 2 in for x. And there we have, the left-hand limit is 7. same thing for the right-hand limit. But we're going to use the equation on the right. That's x squared plus 3. So 2 squared plus 3, that's 4, plus 3 is 7. So in this case, this one and this one match. So far so good, they match. Is the limit the same as the value? Well, when x equals 2, our equation is x plus 5. They all match. So that means that the limit as x approaches 2 from the left equals the limit as x approaches 2 from the right. And that equals f of 2. So f of x is continuous at x equals 2. Okay, let's do a couple other practice problems with continuity. If g of x equals 8, if x equals 4, and equals x plus 8 over 4, if x does not equal 4, is g of x continuous at 4? So remember what's happening with g of x is, so we've got 4 here. Exactly at 4, x equals 8, or g of x equals 8. But when it's not equal to 4, so both on the left and on the right, g of x equals x plus 8 over 4. So when we're doing the left limit and we're doing the right limit, we're using the exact same equation. So what we're finding is we're finding the limit as x approaches 4 of x plus 8 over 4. 4 plus 8 over 4, 12 over 4, or 3. So we've done that first piece. We found the overall limit. Now we need to just compare it to the value of f of x at x equals c. Well, we're told that when x equals 4, g of x equals 8. Notice 8 and 3 do not match. So that means the limit as x approaches 4 of g of x does not equal g of 4. That means the function is not continuous at x equals 4. Thirdly, let's look at one that isn't a piecewise function. Let's say h of x equals x plus 5 over x minus 9. Is h of x continuous at x equals 9? So here we only have one function. Let's get the limit as x approaches 9 from the left. Now notice that if we try to plug 9 in right here, we get we get a vertical asymptote. If we have a vertical asymptote, this automatically means it's discontinuous. Just because there's a value for x that has no y, it's right at that x equals 9, going to be discontinuous. Basically what's going on is it looks something like this. There's a discontinuity right here. If we went on, we could do the full formal definition and say, okay, when we find h of 9, there is no value. If we do the limit coming from the left, then we might very well get we're going to get positive or negative infinity. We do coming from the right, it's going to be the other one. But if we ever have this situation where we try to plug it in, we have division by 0, vertical asymptote, discontinuous. Notice that if we plugged in another value, like x approaches 8 or something like that, if that was the problem, that's not taking place where we're not looking right where this vertical asymptote is. So it might very well be continuous. You have to walk through the whole thing. Similar to this, though, if we have a removable discontinuity, it's still continuous. Is j of x continuous at x equals -3? Well, when we're finding that limit, what we do is we would be canceling this out. But when we're finding j of -3, we're just putting -3 plus 3, -3 minus 3 over -3 plus 3. Notice that we're getting 0 divided by 0. We're not allowed to divide by 0, so it's a removable discontinuity. But it's still discontinuous. It's this sort of shape.